biological and multi-scale communication, IEEE communication letters, and IEEE wireless communication letters. His current research includes 6G and beyond wireless communication, quantum, molecular, and biological communication systems. I welcome you, sir, to this faculty development program on 5G and beyond wireless communications. Hope the participants will definitely get benefited uh, from your expertise.
Thank you
Over to
very
you,
much, sir, for the invitation. Yeah, thanks a lot, sir. So should I start, sir?
Yes, please start, sir.
Yes, sir. Is the screen visible, sir?
Yes, sir, it is visible. Just make it full screen, sir.
Yes, sir.
Yes, sir. Now it is perfectly fine.
Okay. So
You can move.
thanks a lot again to Ravi sir and Nanda sir for inviting me to this FTP. And it is my really I am feeling honored to be part of this, and I look forward sharing my views on next generation wireless uh, communication technology. Specifically, I would be talking about reconfigurable intelligent surfaces, which are potential technology for sixth generation wireless communication systems. We will discuss the idea of RIS, what it is, what are the issues in RIS, and what are the implementation status across the world. So when we say idea, like what these RISs are, passive meta surfaces, then they are used to enhance the coverage, issues, what are the problems related to channel estimation, and prototype real world deployment, like how we can utilize the concept of RIS for improving the performance of next generation wireless comm systems. I am from VNIT, like MNIT. VNIT is also one of the NITs. So this is
Prabhat sir, there is one small request
yes, sir.
that the participants will be interacting with you over chat.
Yes, sir. Okay, sir.
So they will not be on mute and interacting with you. They will be typing their problems in chat. So in the chat box, at the end, you can also take the questions.
Okay, sir.
Okay.
Or I can open chat box.
In the
Yes,
chat
fine, we'll
box,
do.
you can look at the problems.
Right, sir.
They
Thank you, sir.
they will be done that.
Yes, sir.
Please, sir, please go ahead.
So I am from VNIT Nagpur. We were established in 1960 as VRC and later converted to VNIT. We are having 215 acres of area and more than 5,000 students. This is my department, ECE department. We offer BTech in ECE and MTech in communication systems and PhD in all relevant areas. Both our courses, UG and PG, are NBA accredited for full 6 years, and all our faculty members, right from communication to signal processing, biomedical, antennas, in all areas, they are actively involved in R&D and consultancies. The flow of my talk is going to be following. I would start with the evolution from 5G, and we'll take the discussion towards sixth generation. We'll talk about the multiple access techniques and then how we can start redesigning the physical layer of wireless communication system. Then I will touch upon in detail the RIS part. So as we know that if we talk about, let me start with this slide. So the evolution of communication systems from first generation to 6G, we see I have divided the communication components in 4 parts. One is transmitter, channel, interference, and receiver. So, as per these 4 aspects, what were, during the evolution process, what changed out of these 4? For example, when we were having first generation of wireless communication system, the transmitter was standard defined and there was no flexibility in the transmitter. Whatever was defined by the standard, all have to follow that. Channel was random, no control over the channel. Interference, we avoided the interference by operating in orthogonal domains. We'll talk about multiple access techniques a little later. But we, like for example, time division multiple access. If one user is transmitting, the other user will not be transmitting in that particular time instant or time slot. So they both were divided in time, orthogonal time slots, right? So that's how we avoided the interference. And then receiver was also having no flexibility. Whatever was standard defined, we have to go with that. This was the situation in first generation. Second generation, a lower level of flexibility came into picture in transmitter and receiver parts. However, the interference and channel still remained the same. In third generation, we tried to control the interference. The methods, signal processing methods evolved, and transmitter and receiver also, became a bit more flexible. Like standards are there, but still there was a lot of flexibility, like which transmitter, like one component of the transmitter you can connect with the other component, two different makes, different vendors, their brands, their components can be connect with each other. So these kind of flexibility came into the picture. So we were, if you see evolution, we were actually trying to get the flexibility more and more at the user end. In 4G, that flexibility become more. Interference was still controlled and channel was still random, right? In 5G, as we all know, 5G has a modular architecture. We can actually modify our network, or we can make our network for as per the requirement of the user, right? So now at this current stage, when we are in the era of 5G, transmitters and receivers, they have very high flexibility, right? Only few essential rules we have to follow. Otherwise, entire receiver transmitter architecture can be a user centric, like can be specific to particular application or to particular user. Interference, we can now intentionally create interference, or we can now control it to a larger extent, right? We are now in a situation where signal processing and VLSI technologies, we do have good chips, we do have good signal processing architectures through which we can control the interference. What is not there in our hand or in our control is the channel, right? Since the beginning of the wireless communications, the channel is still random. So the target for the next generation of wireless communication system is, now we have achieved the flexibility in transmitter receiver. We have got control over the interference, but we are still looking for some control over the channel. So this aspect is what people are looking for in a 6G communication system. We know, if we talk about the channel, we know that channel is the real villain kind of thing in the entire wireless communication system. Generally, we get doubly selective relay fading channels because of lot of vegetation and urbanization. The channel is highly multipath faded, and most of the times channel can be in deep fade, and getting your message delivered over this kind of channel is a critical task. Right. So before I go for the solution of this, how to control the channel, before I give the idea about that, let us first discuss how the multiple access techniques have evolved over last 20 or 30 years. So initially we started with OMA, which is orthogonal multiple access OMA technologies. So in OMA technologies, we used to divide the resources in terms of orthogonally among the users. For example, if you have time division multiple axis, in time division multiple axis, the time axis was divided among the users. One user will speak at a time, others will listen, and when this slot is over, the next user will come up. So each user was allocated a different time on the channel. This was there in the TDMA. And FDMA was another OMA technology, orthogonal multiple axis technology, where each user was allocated a different frequency spectrum. Like the entire frequency spectrum was divided among the users, and each user for all the time with all the power can transmit within that spectrum, right? So the frequency subbands were allocated to each of the users and they cannot interfere with each other. If suppose this orange guy is transmitting, it cannot interfere with this blue guy, right? So this was what happened in FDMA. And then came the CDMA, where each user allocated a different code on the channel. So time, frequency, and power orthogonality came in terms of code. And then we have OFDMA, orthogonal frequency division multiple axis, where each user allocated a different resource, which can vary both in time as well as in frequency. So time division multiple axis technology, it was orthogonal technology which was used in 1G. This way we were avoiding the interference, right? So first generation of wireless communication systems utilized TDMA. Second generation systems utilized frequency division multiple axis. Third generation were mainly focused on CDMA, and now 4G and 5G systems, they are utilizing OFDMA. So this is how we try to manage the interference in the wireless communication systems. The advantage of orthogonal multiple axis technologies these are having simple transceiver design, because the resources are allocated in orthogonal basis. So there is no provision, or there is no chance of interference occurring, right? So no multi-user interference occurs, and the receiver transmitter design is very simple. What is the drawback of these schemes? The drawback is, if suppose you have very large number of users, for example, this FDMA plot you see, if you have large number of users, with increasing number of users, your frequency requirements will increase, right? You will need a wider spectrum so that you can divide it among the large number of users. Same way, if you have large number of users, you have to divide you have to have a longer time period, and each user will get its time again after long period of time, right? So rate of communication will decrease. Here the bandwidth requirements would be more. So this way, OMA technologies are a bit demanding, right? They are because the number of users, they limit the number of available resources. Hope this is clear. Okay, the next generation wireless systems, they utilized SDMA, which is space division multiple axis. Means we tried to avoid the interference by beamforming the signal at a particular user location. Okay, for example, you see this. Suppose this base station want to transmit to user 3. Now it would be beamforming to this particular user. Because of the beamforming, it is like most likely that most of the signal would be falling upon in the region of user 3 only, and user 2 and user 1 are unlikely receiving any message which is destined to user 3. So still, but like, because it is a physical situation, so there may be some leakage which is coming to user 2 and user 1. In this case, what happens? In earlier case, there was no interference at all. Here, there can be some interference, but the receiver, suppose user 3 is the destined receiver, it is going to treat interference as noise. I hope this is clear. So in SDMA, the multi-user interference is managed by considering the interference as noise. If we talk about the positive aspect of HDMA, again, it has got a simple transceiver design. Only you need to put up the beamforming mechanism at the transmitter and at the receiver. And this also works well for underloaded network. And for beamforming, those who have undergone a course on wireless communication, they may be knowing that for beamforming, we need channel state information. So if the channel state information is known, then at the transmitter side, you can perform the beamforming for a given user. So this method highly depends on the performance of this method depends on availability of channel state information at the transmitter. The drawback of this is it is like sensitive to network load. If suppose there are a lot of users, the number of users are too much, then getting the beamforming, particularly at a given user location, is a difficult task. Again, collecting the channel state information at the transmitter for all the users would be a lengthy process. So this makes SDMA a bit challenging technology to use. Next comes the NOMA, non-orthogonal multiple access technology. So in NOMA, like for example, power domain NOMA, right? So in power domain NOMA, the power domain is used to break the orthogonality, means the resources are now orthogonal in power domain. They are not like they would be transmitting in same frequency, same time, by same antenna, but with different power levels, right? How do we achieve it? At the transmitter side, we achieve it by providing the superposition coding. And at the receiver side, we do successive interference cancellation. So, for example, if this guy is transmitting the message by the base station is for user 1 and user 2 both. So what these messages would be different in? They would be different in the power levels. So user equipment 1, so the upper one is UE2. User equipment 1 will be having this much of power and user equipment 2 would be having this much of power, and they would be transmitted at a single message, right? And the message would be transmitted to this. Now, one of the user will decode it, will decode the interference fully, and other user will decode the interference as SDMA. So this scheme of NOMA, it would be like it would be possible only not only like it would be dependent on the successive interference cancellation method, right? The advantage of this so like NOMA, as I told earlier, in 4G, 5G, we are still looking at OFDMA. NOMA is, although, in the research domain since almost more than a decade now, but we have not received, the confirmation that NOMA would be part of standards so far in 5G. It was included as a study item in 5G, but it was not, converted into the work item. One more point that I would like to discuss is NOMA manages multi-user interference by fully decoding the interference at receiver through SIC, successive interference cancellation. The advantage of NOMA is in overloaded network, it improves the spectral efficiency, but the disadvantage is we need the successive interference cancellation, which is actually a complex task to perform in signal processing aspects, right? And then because at the transmitter side, we have to apply superposition coding, and at the receiver side, we have to apply SIC. So it makes transmitters and receivers more computationally complex, right? It adds the burden and the computational power of transmitter and receivers. Now, if we compare all the multiple access schemes, Okay. Yes. So our point was about the interference. So if we compare, like if we see here in orthogonal multiple axis, the interference was not there. Here the interference was there, but we treated interference as noise, and here interference was there, but we tried to fully decode the interference. Okay. Now, if we think about the next generation of wireless communication system, and what kind of multiple access technology would be required for achieving the specifications for next generation wireless communication system, then we have to think about the technologies or multiple access technology which can not only suppress the interference but also is computationally less burdensome. So as we know, the next generation of wireless communication system 6G, we are going to have internet of everything, means almost everything is expected to be connected to internet. So it will require higher throughput. Ultra reliability, it has already been introduced in 5G, and now we would be having even lower or maybe stringent uh, latency constraint on in 6G, right? Then heterogeneous quality of service would be part of 6G. We are looking for massive connectivity as far as MMTC is concerned, and then the new aspects will come in 6G, which are different from 5G. One of these aspects is sensing and localization. So we would be having the applications like integrated sensing and communication. We would be having as computing, and we would be having control in the network. So these all specifications are expected to be there in the next generation of wireless communication system. The fundamental issue is, if we are increasing the number of users, the interference management will become a crucial task, because with multiple users, the interference will be unavoidable. How to manage it in the network would be a difficult task, right? So what we can do, the network, or as a network designer, we have to decide whether we want to do adaptive decoding or we want to treat the interference as noise. So this is the fundamental issue. For these two aspects, one is to control the channel. As I said, like in 6G, we are looking for gaining some control over the channel. And other aspect is to manage the interference. Now we have to think upon how we can change the design specs of the wireless communication system. So we have to actually look at two different layers. One is the multiple access layer and other is the physical layer. So would be now talking about how we can redesign the multiple access layer and how we can redesign the physical layer. Next couple of slides, I would be talking about one new idea, which is called rate splitting multiple access, RSMA, right? And this RSMA technology is about managing the interference without adding to that much of complexity or computational burden on the system. It will bridge two extremes of OMA and NOMA and SDMA, right? It won't be a kind of resource hungry method. It would be neither. It would be like SDMA, where interference is treated as noise. We are not considering interference as interference, nor like NOMA, where we are trying to decode the entire interference we are trying to cancel. So we would be bridging these two extremes. And then the rest of the part of this talk, I would be focusing on reconfigurable intelligent surfaces, where we would be trying to modify the physical environment, the channel, which has not been under control so far. In the desired way, we want to modify it. So this is going to be uh, the idea about my talk. If you have any questions so far, you can just uh, ask in the chat box. Now I will be starting with RSMA. So what happens in RSMA? In RSMA, the entire message is split into two parts. One is, say, the message for user 1, W1, would be divided into partitioned into two parts. The common part and other is called the private part of the message. So common message and private message. Similarly for user 2 also, common message and private message. Now we will create a global common by combining both of the common messages. So a global common message WC is created by combining W common message of user 1 and common message of user 2. And then what we will do, we will decode WC independently and we'll convert WC into SC, and the personal message of user 1 WP1 we will encode it as S1, right? And personal message of W2, which is WP2, we will encode it as S2. Now we do have three different messages. One is the SC, which actually has the common messages of all the users, W1 and W2. Then their personal messages, S1 and S2. Now these three messages, SC, S1 and S2, these three components would be clubbed together by proper beamforming vector we will apply, and we will combine these three messages, and overall message X would be transmitted combinedly, right? This is what we do in RSMA. Now, at the receiver side, what we will do, we will try to first get out the uh, common part, like which is the common message for all the users, user 1 and user 2. So both the users will try to first decode the common part, and while decoding the common part, they will be treating S1 as noise and S2 as noise. So here they are working as if they are in SDMA, right? Space division multiple axis, where interference was treated as noise. But interference is treated as noise only for SC part of the, only for global common part of the message, not for both. Now, once SC is decoded, then for decoding S1 and S2, we will follow the NOMA process, which is we will apply successive interference cancellation at both the users, and they will try to decode their own. S1 means the personal message for user 1, and S2, which is personal message for user 2. So they will try to do it. By doing so, means some of the part of the message we are decoding as SDMA, and some other remaining part of the messages we are decoding as NOMA. So by this way, we are bridging two extremes, and what we are doing, we are actually splitting the messages in the rate. Means how much message is there in the common message part, and how much message is there in the uh, personal message part. I hope this is clear. If you have any question, please put in chat box. So this is the new multiple axis technology, which is there in the, which is expected to be a part of 6th generation wireless communication system. Now I would be talking about how we can try to redesign the physical layer. The concept is of RIS, which is reconfigurable intelligent surface. So reconfigurable intelligent surface is a planar surface which is made up of metamaterial atoms. So this is the, are you able to see the cursor? So this is the two-dimensional surface where each of these rectangular boxes are metamaterial elements. We call them the meta atoms or unit element of RIS. Now, each of these meta atom or unit element, they have some reflective coefficient eta n, and they have some phase coefficient theta n, right? For nth RIS atom, reflection coefficient is eta n, phase coefficient is theta n. The size of each of these RIS elements is sub lambda, means if the wavelength is say lambda, then the elements are lambda by 2 size or dimensions, or maybe lambda by 5 dimensions. Now It works in the following manner. If you have a transmitter, it transmits some electromagnetic energy. Whatever the energy is falling upon each of these meta items will provide a desired phase shift so that the reflected component of the energy, the entire reflected part of the energy from each of these meta atoms will become in phase, right? So that the energy is beamformed at a user location. So it will act as a mirror where whatever the incident electromagnetic signal is there, that signal would be made beamforming at a particular user. This is being achieved by creating the phase shifts in the response of each of these meta atoms. It's not that we are going in one phase. We can also have the opposite phase, and we can try to nullify the energy at other user also. So essentially, what we can do, we can constructively, we can combine the energy components in a constructive manner so that the signal to noise ratio increases, or we can combine the components in destructive manner so that at the undesired user the energy can be nullified. Okay, so there are two use cases of RIS, reconfigurable intelligent surface. One is for energy focusing, through which we can actually enhance the signal to noise ratio, and other is energy nulling, where the RIS is used to cancel out the signal at any unintended user. So as above use cases, as I described, are achieved by optimally controlling eta n and theta n. That is the response of each of the metamaterial. Now, there can be a question like, is it not kind of multiple antenna elements, a MIMO system, where we are using multiple antennas for beamforming the energy? Yes, Rajeshri. Same question I am about to answer. Means, so my question maybe my explanation may be a bit different, but probably it will we'll see like if you get your answer or not. So if we compare the RIS with massive MIMO systems, the fundamental difference between RIS and any massive MIMO system is the operating mechanism. So RISs are just the reflectors, right? They reflect. Reflectors means we do have just eta n and theta n to control, nothing else. Whereas in massive MIMO, each antenna has got the active transmission and reception with entire RF chain, right? All LNA, power amplifier, everything would be part of the MIMO system. Whereas RIS is not is not an active kind of system. It is just a passive reflection via each of these elements. Signal processing wise, at MIMO when we create, we have full access to baseband, and we do the baseband signal processing. Means we can encode, decode the message. Whereas at the RIS side, we don't have any baseband access. We can't decode or encode the message. We just try to control the phase of incoming signal. If you see the element composition in massive MIMO, there are all ADCs, DACs, right? Amplifiers would be part of massive MIMO. Whereas in RIS, these are just passive meta surfaces which have pin diodes as phase shifters. Typically, half wavelength we follow as antenna spacing in massive MIMO as per Nyquist's spatial sampling theorem. However, in RISs, we can go beyond, even below this, the given spatial sampling, specifications. We can go even lambda by 5 to lambda by 8, something like that. So that rule essentially doesn't apply in RISs. Power consumption in MIMO, it because of active, RF chain, there is higher power consumption in massive MIMO, whereas the power consumption in RIS, it is low compared to the massive MIMO system. In network, the massive MIMO node will act as the source or destination, whereas in RIS, there is no such source and destination. They are just the reflector, which reflect the incoming signal at a desired location, right? And cost-wise also, massive MIMO, because of the amplifier, LNA, entire RF chain, massive MIMO systems are bit costly, not bit costly, they are actually costlier systems, whereas RISs are low-cost system, but the cost may increase if you are increasing the number of elements in RIS. So hope, Rajashree, your question is answered. If you have any further question on this, we can. Is there any other question you can answer in chat box? Okay, thank you. Now, there is a concept of relay in cooperative communication. So, how RIS is different from any cooperative relay? So, I will just summarize the differences between a relay and RIS. Again, relay is also not like MIMO, but it is also having active receiver or transmitter elements. RIS, no active element. Signal processing, relay can decode or amplify. Like we have those who have, knowledge of cooperative communication. There are multiple types of relays, amplify and forward relay, which can first receive the signal, amplify it and forward it, right? And decode and forward means the relay will first receive the signal, will try to decode it out and will transmit forward the decoded version, right? So relay has to receive and it has to access the baseband of the signal so that it can decide, decode and amplify the signal. Whereas RIS doesn't need any such baseband availability. Duplexing, relay can be full duplex, half duplex. RIS is generally full duplex. As I said, baseband access is not required in RIS, but it is required in any relay. The power consumption is high in a relay due to the active RF and baseband elements, whereas the power consumption in RIS is low. Specifically in passive RIS, it becomes bit comparable if you are having active RIS. Latency is high in relay because it has to access the baseband and process it, whereas RIS is simply reflecting, so no latency introduced by, or no or very less latency is introduced by the RIS. The cost also very high in relay case and low in RIS case. So these are the differences between RIS and relay. Now, if we are talking about redesigning the physical layer, we can use the RIS because we can have some control over the channel. And unlike multi-input, multi-output MIMO systems and cooperative relay, RISs are quasi-passive. They have low power consumption. They are having low thermal noise. I will discuss these parts in detail. There is, RISs are software programmable. We do have controller circuit which we can program. They are easy to deploy and they are band flexible. Band flexible means you can have RIS for microwave RF frequencies. You can have RISs for millimeter wave and even for terahertz frequencies. We can design RISs and can even nowadays people are designing RISs for visible light communication systems. RISs are of two types. Actually, it depends on how we are looking at this classification. So RISs can be active or passive. In most of this talk, I would be talking about passive RISs, whereas active RISs are also being researched upon these days, where they are putting up some active elements in the RIS and they're trying to see the signal where it is from, where it is coming from, and amplify it. That also is being researched upon. Now, RIS has been included in the agenda item of all these standardization agencies. ITU, 3GPP, I will discuss on that. And we are trying to use RIS for localization and for sensing purposes. So mathematics, if I just want to, I'm not going into much of the maths, but just would like to highlight some of this thing. So this RIS, each element is having the response eta n and theta n. The channel is Gn from nth element to the receiver. The channel from this transmitter to the nth element is Hn. So overall end-to-end channel will become eta n Gn exponential j theta n into Hn. Right? Now this is the entire channel. Now whatever you will transmit over this channel X, it would be like this, Hx plus some noise. Now, for coherent beamforming, this guy has to get the maximum value, and the maximum value is achieved if the theta n compensates the channel gain, channel phase of Hn and Gn combined. So, if you set theta n to be in such a way that it cancels out the summation of phase of the G channel and phase of H channel. So, if you can provide that phase shift, then you can achieve the maximum SNR, and that SNR would be directly proportional to n square, because there are n number of elements in the RIS. So n square would be the gain in the SNR. This is what the basic fundamental math working of the RIS element. I hope this is clear. Is there any doubt before we move ahead? Please let me know. You can type in the chat box. Okay, I believe no doubt. So let us go ahead. So RIS is one of the potential technology. ITU has included it in its IMD 2030 document, which is kind of a vision document of ITU, International Telecommunication Union. It's been part of now 3GPP discussions, ETSI discussions. ETSI is European Telecom Standardization this agency, and TSDSI, right? So this is Indian agency which is responsible for standardization, and in TSDSI also RIS is part of discussion. Now, I'm not sure if you guys are interested in all this maths. So maybe I will skip this maths. Or we can come back to it later. Just couple of results, like if I would like to tell. Yes, so if you see the outage probability or error probability for different RIS element, as you are increasing the number of elements, the probability of error or outage probability reduces drastically. And it is not like a coding gain kind of system. You are getting gain in the slope, right? Slope is your outage probability is decreasing faster, at a faster rate, faster slope, compared to what you were getting in the higher, lower number of elements, right? So this is one of the idea. And like, what is the effect of the optimal phase, at RIS element, means is theta n actually uh, reducing or actually compensating the HN phase and GN phase. So if it is an optimal phase, then we are getting the best performance, right? And if the phase is coupled to like the receiver, then we are getting the best performance. If it is not coupled to the receiver, but it is a coupled phase, you are getting this performance. And if it is if it is not coupled, you are giving just a constant phase, then your performance is this one. So the way you are handling the phase you are providing through RIS, it makes a lot of difference, right? And it is crucial for RIS performance. This is for different channel conditions. If you have LOS and if you have non-LOS situations, then how RIS can improve the system performance. So you see, as I said earlier, it's not just the gain reduction in the probability, but it is also the change in the slope, right? So slope is changing as you are putting up more number of elements. We compare the performance of RSMA, NOMA for transmit user and receive user, and we found that RSMA performs better than NOMA even in presence of RIS. So RIS and RSMA combinedly can become a good candidate technology for 6th generation of wireless communication system. So RSMA can serve at MAC layer and NOMA can serve at physical layer. I hope this is clear. Now, before moving ahead, let me just ask if there is any question. Okay, so if there is no further question, let me just start the more detailed discussion on RIS. So far, we have seen how RIS works and how much performance gain in terms of outage probability or error probability if you are deploying an RIS into the wireless communication system. Now the question is RIS really intelligent? So common assumption, in fact, in its name also, reconfigurable intelligent surfaces. So RISs are labeled as intelligent because they can reconfigure the electromagnetic wave and reflection, incoming reflection, they can reconfigure. But are they really intelligent? Answer is most of the existing RISs are reconfigurable, but they are not intelligent. So from where you will bring this intelligence into it? So you have to bring in the AI aspects in the RIS. You have to bring in the deep compressive sensing, which can reduce the pilot overhead for CSI acquisition. Generative adversarial networks, GANs, can also be used for generating synthetic channels and reducing real-time estimation needs. We can have deep reinforcement learning, which learn optimal beamforming strategies directly based on the feedback, which is not requiring any channel state information. So using artificial intelligence and machine learning tools, we can make the RIS actually intelligent. The question is RIS really intelligent? The answer is RIS by itself is not intelligent. We have to make it intelligent. Okay. So in order to make it intelligent, we have to integrate artificial intelligence into the system. Next is RIS noise modeling. If you see, I also have spoken in earlier slides that RIS it provides very less noise or no noise, but it's not the case. The myth is RIS introduces negligible noise due to passive operation, but the reality is the thermal noise is existing whenever RIS is performing its operation, and that thermal noise becomes significant if you have RIS at a large scale. Means if there are large number of elements, then this thermal noise can be a crucial factor. Like it can affect the system performance significantly. So for 10,000 elements, where RIS is operating at 100 megahertz band, the signal bandwidth is 100 megahertz. In that 10,000 element RIS, it can introduce minus 54 dBm of noise, right? And if you add 30 dB of path loss, then you can, at the receiver side, can experience as low as minus 84 dBm, which is comparable to the receiver's natural noise. So this way, if we say that RIS is noise free, this is not a correct statement. RIS can have noise, and that noise can be significant for larger number of RIS elements. Hope this is clear. Now, I said in the earlier slides, maybe you can go through here, that the signal, if we achieve the coherent beamforming, we can achieve the signal to noise ratio, which is proportional to n square, means n is the number of terms. So n square times SNR we can achieve at the user location. However, in reality, the answer is we generally do not achieve n square times coherent gain, but in practical, as at BNID, we have fabricated RISs, we have implemented the entire wireless communication setup. We could see that practically SNR goes like n or say 1.5 times n, but not like proportional to n square, right? So square law gain, which we discussed as mathematical aspect, is actually a theoretical thing. It is idealistic phenomena, and the performance Pluto, it occurs due to physical limitations like the spacing between RIS element, the material which we are using for RIS, the leakage, so many physical factors, they reduces the these factors reduce the performance in terms of SNR gain of RIS, and we actually do not achieve the theoretically claimed n square gain in the SNR at the receiver. Now there are two structures of RIS. RIS is not just a reflective structure, it can also have transmission and reflection both. So those RISs are called simultaneously transmitting and reflecting RISs. So these RIS, one side they can reflect to, and other side user they can transmit through. And that way we can enhance the indoor coverage by putting RIS into building walls. And it can also improve the spectral reuse by supporting multiple spatial zones. The benefit of this is it can improve the spatial resource utilization and environmental adaptability. Now, there is another claim. There is a myth that RIS consumes near zero power. As I said, while comparing RIS with massive MIMO, that RISs, they are massive MIMO systems, they are more power hungry compared to RIS. That is a truth, but it's not like that. RIS is actually power. It doesn't consume any power. RIS also consume power. They need power for their controller circuit, right? So there is a question like, simulation and testing of RIS is possible? If so, which is in which tool? Okay, I'm coming to that. I will be telling you what we have done at VNIT. Maybe like we can go to that and we can discuss it in more detail, right? So, Nanda sir, can we give them the mic access? Like if you want to have interaction? Okay, let's see. So RIS also consumes some power. For example, if it is a 1600 element, then it requires around 11.2 watt of power, right? There are other hidden costs also, like beamforming design patterns, and then the cost for CSI acquisition. You have to put up more signal processing elements for that. So the conclusion is the practical RIS deployments, they should be evaluated not just for the passive power consumption, but overall total power footprint in controller circuit, in CSI acquisition, total how much power they are consuming, it should define the overall power consumption of RIS. Now, active versus passive RISs. So, as I said, there is a noise component in active RIS because it has access to baseband and thermal noise comes into the picture. Nowadays, active RISs are also becoming a lot of hot research topic. But most of the work that we have done at VNIT are focused on passive RISs. So I would be talking more on passive RISs. However, active RISs, they provide 124% sum rate gain, whereas passive RISs just provide 21% sum rate gain. But this is more power consuming and it is a bit more closer to the passive MIMO part, right? So it's not like like the only reflective elements, they are having active RF chains also. So there is a beamforming complexity. Like if you have large RISs, you have to, acquire RIS. We have to acquire RIS for uh, channel estimation. So if there are large number of elements, we have large number of channels. For each channel, we have to estimate the channel coefficient. So channel coefficient estimation will become a tedious task for a larger size RIS. So there is a code book based method, which in RRIS we have used the code book based method, and we found that code book based method is more suitable for practical practical deployments of RISs. Now, just to quickly revise what we have seen so far is the summary of what we have discussed. RIS versus massive MIMO. So RIS is passive, cost effective, and energy efficient, but it lacks baseband processing, and it is not active as MIMO. RIS versus relay. RIS only reflects with phase control. No decoding or amplification is possible in RIS, like in AF and DF relay. Is it just reflective? No, RIS can be transmittive also. We can have different types of RISs. Are RIS is fully passive? Yes, if you are making it passive, but there are now research going on where people are making active RISs. Is RIS noise free? Answer is no. RIS also generates some noise. Does RIS provide the square law gain? Answer is in theory, yes, but in practice, it doesn't provide a square law gain. Is RIS truly intelligent? Answer is no. By itself, it is not. We have to enable RIS through artificial intelligence, and then it can become intelligent. Is it like the beamforming pattern is efficient? So answer is there are two approaches, CSI based approach and codebook based approach. So CSI based method are complex and they become more complex if the size of RIS increase. However, the codebook based methods are practically more feasible. Power saving in RIS, they need power only for controlling of the elements. And if you have more elements, the power consumption or power budget would be more. So this is what we have discussed so far in terms of RISs. Now, some research use cases of RISs. Maybe this is, I will quickly cover it and I will try to go on to the work that we have done at VNIT. So we can use RISs for millimeter wave systems because millimeter wave systems, they are highly they require line of sight because millimeter wave means you have very less wavelength, lower wavelength. So if wavelength is lower means signal dimensions are less and signal can be affected by even some obstacles, right? So in those cases where the signal is affected or to maintain the line of sight in millimeter wave, you can deploy RIS. Even in multi-cell networks where you want to provide, you want to increase the sum rate at different users, you can use RISs. So all these are, potential PhD problems. Those faculty members or students who are looking for problem in RIS, they can think of these things. Then we can use RIS in SWIFT, which is simultaneous wireless information and power transfer, where like in IoT devices now they have to, operate. IoT devices have to harvest the energy by their own. Otherwise, battery recharging battery is bit difficult. So for that purpose, Swift can be a good idea, and RIS, by putting up more signal strength, some power can be used for decoding and rest of the power can be used for harvesting. That way RIS can help. Then for mobile edge computing systems also, RIS can be used and it can reduce the task latency from 115 millisecond to 65 millisecond if you are using 100 element RIS. So RIS can also be beneficial in those tasks. NOVA, you can use RIS, then multicast network, physical layer security, and in cognitive radio also, RISs can be used. So these are the research topics. Now I would be talking about what we have done at VNIT. So is there any question or some discussion so far? Any participant? Okay, I don't know whether there are questions. Okay, so would like to give you some idea about my lab at VNIT. So we have in the year 2023, we have successfully implemented the working prototype of RIS assisted wireless communication system. It was first prototype in our country, and we demonstrated at India Mobile Congress 2023 at in presence of Prime Minister in New Delhi. So this is the RIS that we made. This is the entire transmitter receiver circuit. So this is the RIS. We have the controller circuit behind it. This is the transmit horn antenna, receive horn antenna. Then we do have USRP setup, and we transmit it. We transmitted the 64 QAM system, and the data rate that we achieved, throughput that we achieved using RIS was 37.61, and this was achieved when we maintained that there is no direct line of sight apart from RIS between transmitter and receiver. The SINR gain was 27.41 dB, and the VLER was almost zero, and we were achieving very clear constellation diagram, right? And when we have off condition of RIS, the constellation diagram was noisy, and BLER was almost 1, right? And data rate was 0. And outdoor also we did the RIS testing. We had tested the RIS in outdoor environments. And anechoic chamber also we tested our RIS, and it was found working well. We demonstrated at IMC 2023. Then the improved version of it we demonstrated at IMC 2024. And then we have some comparison with other RISs in the world. So our RIS was at 5.3 gigahertz. We have 400 elements, 1-bit RIS. We use pin diodes, and for controlling method, we use microcontroller based shift register. And we achieved the highest throughput among the existing RISs, which was around 37 Mbps, right? So this was the performance of VNIT's RIS that we made in 2023. And we also tested this RIS for near field in our anechoic chamber. So we found that RIS is working as expected in near field also. Now we have this multiple RISs now at different frequencies. We have a startup. You can contact us at, I will provide you my email ID. We can provide you the RISs. We can help you design RISs, test RISs. at different frequencies for different number of elements. And we do have now dynamic beamforming of RISs. Okay, so whenever user would be moving, the RIS would be reflecting to that particular user location. So RIS by itself will be doing this task. So this is our company name, Sarvaksh. And what we are doing at Sarvaksh, we are now trying to, we have all RIS solutions. Now we are trying to include the RIS in part of 6G as enabler for integrated sensing and communication systems. We are incorporating artificial intelligence and machine learning. So in fact, some of you who are looking for internship or job, specifically the masters or PhD students, those who have idea about RISs or maybe IAI or ISAC, some good background, you can contact us. We would be happy to discuss it further. So research applications we have already discussed. So we are open for collaborations on analytical part, AI ML based use cases. I can just show you what we have achieved so far in terms of publications. So we do have ongoing projects of around 7.8 crores. We have more than 125 publications, more than almost now 3,000 citations. Our impact factor is 500 plus. We published in all top journals like TCOM, TWC, TWT, TVT, wireless com letters. And we have strong collaboration from USC to Queen Mary to different IITs. So we would be happy to discuss any possible collaboration on RIS or AI assisted RIS systems. You can reach out to me at this email ID. This is PRABHAT Prabhat Sarma, and this is ece.vnit.ac.in. So thanks. This now I am open for question and answers.
Hello,
Yes,
am I
please.
audible, sir?
Yes, you are audible.
Sir, this is Rajeshri from IIIT Bhubaneswar.
Yeah. Hello, Raj.
Sir, presently I am working with MIMO antenna design
Okay.
actually, and I want to do a recompatible MIMO antenna. So that's why I just want to ask: is the RIS surface work together with antenna, or like meta surface we are simulating it differently? Like this also will simulate RIS surface, then we add antenna and all that. This is my question, sir.
So RIS is just a kind of lens, right? MIMO, it can also assist the MIMO wireless communication system where transmitter is MIMO or receiver is MIMO system, right?
Yes, sir.
So that is possible. So you have MIMO at the transmitter and the receiver, and you are
Yes,
putting
sir.
RIS. So RIS would be just reflecting whatever is coming from the multiple antennas of transmitter. So one
Okay,
way
sir.
of looking at it this. Other way is you can put up the active antenna elements in the RIS itself, right?
Yes, sir.
So that is something new direction. I have not worked in that area, but I believe that people are now exploring that part. So maybe you can look up into the recent literature and
Yes,
can
sir.
get the ideas.
Yes, sir. Okay. Thank you, sir.
Is there any other question? So my email ID is there if you have got any other question or want to connect on RIS part. So would be happy to interact with you all. So if there is no question, should we conclude the session now? Thank you, sir. Thanks a lot. You guys attended my session, and I look forward to your feedback, or maybe we can connect for some collaboration. Thank you.